Now, in this video, we're going to take up one more problem. Draw problem number 29. It reads as, draw the SFD and BMD for the loaded beam shown in figure. Mark the salient points, locate the maximum bending moment and the point of counterflexion. So here we have a beam having 5 meters length, having at point A, it's a clockwise couple of 500 kilonewton meter. At the point B, to C, you have a uniformly variable load of 0 at B and 50 kilonewton per meter at the point C for a span of 1 meter. And at point D, you have 100 kilonewton acting downwards at point E, between E and F, which is 50 kilonewton per meter for a span of 1 meter. Now we want the support reactions is at the point B and E. Let RBV and REV are the support reactions. Now first we need to understand what will going to be the direction. Initially we will going to take the support reaction at the point B and point E as the vertical reaction acting upwards. Now first we will go for the support reaction. Taking the moments about the point B, then what happens? So that will be equal to REV into 3. So that means this REV into the distance is 3 meters will be equal to, so clockwise couple. So which are the counterclockwise 500 kilonewton meter, then half into area of the triangle, 50 into 1 into distance of center of gravity from the smaller end is 2 by 3 into 1. So 50 into 1 into 2 by 3 into 1 plus 100 into 2 plus 50 into 1 into 1 by 2 plus 3. 50 into 1 into 1 by 2 plus 3. So on simplification, you will going to get REV will be equal to 297.22 kilonewton. So then we need to consider what will be the support reaction at RBV. So to find out that, so sum of the vertical reactions acting upwards will be equal to sum of the reactions acting downwards. So also RBV plus REV will be equal to area of the triangle, that is half into 50 into 1 plus 100 plus 50 into 1. So on simplification, RBV plus 297.22 will be equal to 175. Therefore, RBV will be equal to 175 minus 297.22. So therefore, RBV will be equal to minus 122.22 kilonewton. So since it is a negative value, therefore, in the support reaction at RBV, instead of going upwards, it will be coming down. So that is why it is shown with the reaction acting the downward direction. Now, RBV will be equal to 122 kilonewton acting downwards. Now, we are going to take up the shear force diagram. Once we are considering the shear force diagram at the point A, which is 0, because the couple will not be considered for the shear force. Shear force at the point B will be equal to, between A and B, as there is no load acting, so it will be 0, and SF at B will be equal to 0 minus 122.22, which will be equal to minus 122.22 kilonewton. So which is acting downwards. Now what will going to be the SF at C? SF at C will be equal to minus 122 minus half into 1 into 50. So that will be equal to minus 147.22. And this variation, as it is been with respect to uniformly variable load, the line joining between B and C will be a parabolic curve. Then between C and D, shear force between C and D will be remains constant, because as there is no other load between C and D, so it will be minus 147.22 kilonewton. So SF at the point D will be equal to minus 147.22 minus 100. It will going to be minus 247.22 kilonewton. Again, between D and E, as there is no other load, so it will going to remain constant at minus 247.22 kilonewton. SF at V will be equal to minus 247.22 plus 297.22, which will be equal to plus 50 kilonewton. SF at E. Then SF at F will be equal to plus 50 minus 50 into 1. It will be equal to 0, because as there is a uniformly variable load between E and F, starts from SF from plus 50, joins to 0 by a linear line. So this is how it will going to takes the graph or the plot. So here SF at between A and B, as there is no load, it will going to be remain same between A and B, it remains 0. At SF at B, due to the point load which is acting downwards, it becomes minus 122. Between B and C, since it is a parabolic, since it is a uniformly variable load, you will go to get a parabolic curve. Between C and D, it remains constant because as there is no other load, so it means 147.22. And SF at D, which because due to the 100 kilonewton acting downwards, it's going to further drops down from 147.22 to 247.22. Between D and E, as there is no other load between D and E, it remains constant, that is minus 247.22 kilonewton. And SF at E, as the point load is acting upwards, so naturally this is minus 247.22 plus 297.22, which will going to become plus 50 kilonewton. So because due to the point load at the point E, the SF varies, SF increases from minus 247.22 to plus 50 kilonewton. And between E and F, as there is a uniformly variable load, it varies from plus 50 kilonewton to 0 at the point F. And the line joining between these two will going to be a linear line. So that is what we have explained here. Between A and B, it remains 0. So then it will be minus 122 kilonewton to 147.22 kilonewton parabolically. And between C and D, it is constant at minus 147.22. SF varies from plus 50 kilonewton to 0 linearly. So now we will go for the bending moment diagram. So the bending moment diagram at the point A, which will going to be a clockwise bending moment at the point A, since it is a couple at the point A, since it is a clockwise, it will going to be a positive. So BM at A will be equal to plus 500 kilonewton meter. And BM at B again, it will going to be plus 500 kilonewton. And BM at C will be plus 500 minus 122.2 into 1 minus half into the area of the triangle, that is minus half into 50 into 1 into 1 by 3 into 1. So on simplification, you will going to get it as plus 369.45 kilonewton meter. So it is at this point. Similarly, BM at the point D now. BM at the point D will be equal to plus 500 minus 122.22 into 2, then minus half into 1 into 50 into 1 by 3 plus 1, minus half into 50 into 1 into 1 by 3 plus 1. So BM at D, you will going to get that. That is plus 222.22 kilonewton meter. And BM at E will be equal to, again, plus 500 minus 122.22 into 3, because that from this point to E, we need to consider 1 plus 1 plus 1, it becomes 3. Then area of the triangle, again minus half into 1 into 50 into 1 by 3 into 1 plus 2, then minus 100 into 1. On simplification, you will going to get it as minus 25 kilonewton meter. BM at F will be equal to 0, because BM at F will be equal to 0. That is again plus 500 minus 122.22 into 4 minus half into 50 into 1 into 1 by 3 plus 3. Then minus 100 into 100 into 2. Then plus 297.22 into 1 minus 50 into 1 into 1 by 2. So therefore, you will going to get that value will be 0. So BM at E will be, BM at F will be equal to 0. Now we will go for the BM at F, which will going to be 0. So here we got both the shear force and the bending moment diagram, which I told here, plus 500 minus 122.22 into 4 minus half into 50 into 1 into 1 by 3 into 1 plus 3. Then minus 100 into 2 plus 297.22 into 1 minus 50 into 1 into 1 by 2. That will be, again, it becomes 0. So here, since between E and F, it is a UDL, so it will going to be a parabolic curve. So the maximum positive bending moment will be at the point A, wherein you are going to have the positive bending moment of 500 kilonewton meter, and the maximum negative bending moment is at the point E, where it will going to be minus 25 kilonewton meter. Then between B and A, it is constant because BM varies from 500 kilonewton meter to 369.45 kilonewton meter because it is a cubic curve, because area of the triangle and into distance of center of gravity from the bigger end. So that is area is meter square into distance of center of gravity is in meter. So it becomes meter cube. So therefore, according to that, it will going to have a cubic law. Then BM varies from plus 369.45 to 222.22 kilonewton by means of linearly. Between D and E, it varies from plus 222.22 kilonewton meter to minus 125 kilonewton meter linearly. That means the bending moment is changing its sign from the positive to negative here, which is at the point G. And again, BM varies from minus 25 kilonewton meter to 0 parabolically because due to uniformly distributed load. Now, as the bending moment is changing its sign from the positive to negative here, so therefore you will going to get the point of counterflexion. It is the point where the bending moment changes its sign. Let G be the point at a distance of x meters from F, where the bending moment changes its sign. So BM at G, the magnitude of the BM at G will be equal to 0. So that will be equal to minus 50 into 1 into x minus 1 by 2, because the distance from here, this is the xs, the total distance is x. And so what I want is, I want 50 into 1, that is the UDL for the entire span, into the distance from the midpoint of this UDL to this distance is the one which I want. So 50 into 1 into what is this distance from F to the midpoint? It is x minus, that is half. So I want from this point towards the left side, from this point towards the right side is half, that is 1 into 1 by 2, that is half. So x minus half is this distance into x minus half, plus because it is acting, the load is acting from the upper direction. So actually it becomes sagging. Therefore, plus 297.22 into x minus 1. So on simplification, you will going to get the value of x as, that is minus 50 into x plus 25 plus 297.22 into x minus 297.22 will be equal to 0. Therefore, if you calculate that, 247.22 into x will be equal to 297.22. So therefore, x will be equal to 1.1011 meter. Therefore, the point of counterflexure of the point G will going to be at a distance of 1.1011 meter from the free end at the point F. So this is how you will be able to analyze the bending moment diagram and also the shear force diagram. Thank you.